I'm here to talk about the design and scale and performance of the MapR distribution for Apache Hadoop. I'm the CTO and co-founder of MapR, and we'll quickly go through the outline of the talk here, which is what does MapR do? Just explain real quickly what it is. We are fairly new to the game. So why did we build this? What prompted us to go and build a completely different thing here, more or less completely different? We introduced something called a distributed name node. So I'll discuss the architecture, why we came to that conclusion, what affects its scalability, what's the programming model, and how we put things together with distributed transactions, and we'll see, does this really perform well? So what is MapR? MapR provides a complete distribution. It's fully integrated, tested and hardened with Hive, Pig, Mahout, cascading, Uzi, Scoop, Flume, everything. We replaced, it's very easy to use. I think you should just try it. It's free, it's available for download. And there are some unique advanced features in it, things like snapshots, mirroring, fully reliable, complete read-write system. It's 100% compatible with Apache Hadoop. That is, you can just, it's binary compatible. You can plug it, just put it in there, no need to recompile your applications, it just runs, and you get benefits of its features. So today, it's a 30-minute talk, so I'm going to focus on the lockless storage services and how did the distributed name node, how is it built. So just as another overview of what is MapR, our engineering is divided into all these different pieces. We work on HBase, MapReduce, the system management to make it easier, storage, as well as the rest of the ecosystem, things like the different languages. So like I said, today's talk will be on storage services. So when we started this company, we said, let's look at how to do this work. And the first step was to look at a bunch of JIRAs that were open and see there's some fundamentally difficult things we can solve here. And so I'm not going to go through the JIRAs, but there were some that were being open for, pretty much they were open when we started the company. They're still open today. Things like there's a streaming performance problem and scalability issues, and I think people are very familiar with these things, so I just won't go into these. So we took those JIRAs and spoke to a bunch of customers and said, hey, are these real? I mean, are these really problems we should be addressing? And so the chart out there on your right shows what if you have hardware that can do about 1 gigabyte a second, HDFS does about 200 megabytes to 300 megabytes a second between read and write. So people said, hey, it's not hardware efficient. There were scaling problems. There was a name node bottleneck that's well known. Federation tries to address some of it. There's a big known about the limited number of files that HDFS can support. The admin overhead is significant. When things go wrong, you don't know what exactly happened. Name node failure loses data. So what's happened is people have not trusted HDFS as a permanent store in many cases. This is what people have told us, is the observations. It's a write once kind of system. So if you're writing a large file, unless you close the file, all the data is lost. So if you've written like a couple of gigabytes and something crashed, well, you just lost a couple of gigabytes. And so they introduced this hflush hsync, but it can still lose data because it really doesn't make it to disk. And it required a rewrite and a lot of apps to make use of it. So we said, hey, some of these, we looked at the problems. We said some of these are architectural issues, and the change at that level is a very big deal. And how do we get this change accepted if we try to propose it? So we said, why don't we build it and see if it actually works? And if that happens, then then maybe it'll get accepted better. And so that was our approach. So basically, build it and prove it. And the goals were to improve reliability significantly, make it very fast at the same time, and enable a new class of apps. For example, for real-time analytics, not only do you need to be fast, but you also need to be highly available at the same time. So we'll do a quick review of the HDFS architecture. In HDFS, files are broken into blocks, distributed across data nodes. The name node holds in memory directories and files in the block locations. And the data nodes serve blocks. And they have no idea really about files and directories. So all file directory operations really go to the name node. And that's been one of the biggest source of the problem here, which is empirical traces have shown that over 60% of the operations in a file system are metadata operations. So that has become a single bottleneck right now. The other issue is these block reports, which Suresh just discussed. The data node reports its blocks to the name node. And a large data node can do about 60,000 blocks per report. So if you say a block size is 256 meg, and there are 60,000 of these, you can address about 15 terabytes in a box. And you can buy a modern box with, let's say, which is the equivalent of 5 disks at 3 terabytes per disk. So if you have a modern box with 12 drives or 24 drives, pretty much your utilization is about 40% of what the box can actually hold. And we did some experiments and found that at 100K blocks per report, it causes extreme load on both the data node and in the name node. Both of them kind of. And the way the name node builds its data structure is really by these block reports that are sent periodically. And it takes a while to build up a large data set. The other architectural issue was that the addressing unit is an individual block. So this is the problem. The data node is forced to send giant block reports. Second problem is that the name node can only hold about 300 blocks maximum, so it limits the cluster size, 300 million blocks maximum. So if you multiply those two, you get about 10 petabytes. And if you try to increase the block size to store more stuff, you negatively impact MapR's performance because you don't get parallelism anymore. So basically, how do we scale this? So we came to the conclusion that central metadata servers don't scale. So let's make every server a metadata server. But we need memory for MapReduce. So we have to page this to disk. We wanted to reduce the size of the block reports while increasing the number of blocks per data node. So is there any way to do that? And reduce the memory footprint of the location service so that, after all, you cannot keep on adding memory to a box. It's going to eventually blow up. And there's only so many DIMM slots. And you need really fast restart, because if you want to be highly available, fast restart is extremely important. So we set ourselves pretty lofty goals. We said, number of files, let's make that 1 trillion files. We want to scale the data to about 10 exabytes without a problem. So take it 1,000x. Take the number of nodes to, let's say, 10,000 in one system. And then let's do this with fully random read-write semantics. So you can write randomly, read randomly. So you can do things like export it via NFS or other different protocols. Add enterprise class reliability with snapshots, mirrors, instant restart, and so on. And run it close to hardware speeds. That is, when you're running on really large scale, your efficiency matters even more, because any bad code is now magnified 1,000x. And we want to exploit emerging technology like SSD and 10 gig. And if you don't run close to hardware speeds, you're not going to be able to exploit it. So how does the MapR's distributed name node work? Basically, files and directories are sharded again into blocks, but we place them into mini name nodes called containers on disks. So as you can see, there are 3 files, and the green little shards can all go into the same container. And each of these mini name nodes contains directories and files and blocks. So it's completely whole. It's replicated on the servers. And these are about 16 to 32 gigabyte segments placed on various disks on different nodes, and they're replicated. So in a large cluster, you might have 50 million or 100 million of these containers. But you don't manage them directly. You use MapR volumes to really manage them. So we added this thing called volumes, using a familiar concept from pretty much how you mount files and directories in Unix. Basically, when you have a large 1 trillion files, you cannot do policy on a file level like today, replication factor and so on. You cannot do policy in a directory, and you cannot set policy on the whole cluster because it's just too big. You need something intermediate, and so that's why we came up with volumes. And we let you create up to 100,000 volumes without a problem, and just so create as many as you like. So how does this whole system work? In the MapR distributed name node, containers are tracked globally The clients cache containers and server information for extended periods. And the client can talk to any server and do a read. But there's a name node map that keeps track of all the containers and their server locations. So if the client has a cache miss, it talks to the name node map, fetches the container locations, and contacts the server to read it. So why does this scale really well, doing something very simple like that? Each container represents about 16 to 32 gig of data, and each can hold up to 1 billion files and directories. So on a 1,000-node cluster, I can do 1 trillion files without a problem, firstly. Secondly, all I need is 100 million containers to represent about 2 exabytes, which is a very, very large cluster. In the name node map, I need about 250 bytes of DRAM to hold a container. So we need about 25 gig to represent the 2 exabyte cluster. But we can actually page it to disk. And a typical large 10 petabyte cluster needs only about 2 gigabytes of DRAM to hold it all in memory. And this is the other crucial thing. Container reports are about 100 times to 1,000 times smaller than HDFS block report. So a container report processing is almost instantaneous. A typical box with about 36 terabytes of disk will have about 1,000 containers. So you have 1,000 entries that you're reporting. So conversely, you can serve about 100x to 1,000x more nodes. And if you want to increase this, you just happily increase the container size, and we get a 4 exabyte cluster without really affecting the block size. So MapReduce is not really affected. And we made it very, very simple. This is what it takes to install one of these things and run it. One command, apt-get install or yum install or whatever. Compare that to, for example, Apache Hadoop, where you have to really go through a big set of steps, to set up Linux DRDB and so on. So I'm not going to focus too much on that. So the next thing we looked at was how to actually implement this. And we stepped back and said, hey, there's been a big hardware disruption here. Everything has gone 100x to or larger in the last 10 years. 128 cores are common. 10,000 nodes in a cluster are going to be common. So how do we design something that has no spin locks and no mutexes? We need about 10,000 threads per process. For example, you take a snapshot. You're going to contact all 10,000 nodes. And you need that many RPCs outstanding at once. You want a minimal footprint, because every node is going to be a data node and a name node. But you want to preserve the resources for the app and not run your system on it. And we want rapid rereplication, because when you have when a box with 36 terabytes goes down, you want to be able to re-replicate it very, very rapidly. And that's what is needed. So we decided to do it in C++. And we built an asynchronous programming model. So for example, a call like IO manager read provides a callback function and a void star arg, and the callback is invoked when the read completes. And the model is that we have one OS thread per CPU core, and the dispatcher just maps the container ID to a queue ID, and the queue ID is mapped to a CPU core. And the callback is guaranteed to be invoked on the same core. So you send requests to a queue, and it replies back on the same queue. So no mutexes are necessary, because we guarantee in the framework that you're running on the same core. When load increases, we can add more cores and move some queues to it. We implemented state machines instead of normal threads. And so a thread stack is really a state machine, which is about 4K. So to implement 10,000 threads, if I do the normal Java thread, it's a megabyte each, I would need 40 gigabytes of memory. So here we're doing it with 4K each, and we can do about 10,000 threads in 40 meg. And the context switch, since it's a state machine, is 3 instructions. In fact, the entire scheduler is about 10 lines of code. And we can do about 250,000 context switches per second per core without a problem. So the other question was, well, do we do this in the kernel or in user space? Whenever you start a project, you say, all right, let's get into the kernel and hack there. But here, we wanted to avoid system crashes. There was enough in the modern Linux to be able to do this entirely in user space and not sacrifice performance. And we decided not to use any of the system, the Linux system VM or other things, because we want to preserve that for use by the MapReduce application or by HBase or whatever. So we use only about 1/5 of the system memory. We run really on 1 or 2 cores and leave the others. And the emphasis on efficiency, extreme efficiency. So we work directly on raw devices, do direct I/O, don't use a Linux VM. And at the same time, we implemented CPU and memory firewalls. Since we were screwing around with the memory system anyway, we said, why don't we implement this? And so runaway tasks can no longer bring down your data node or your name node. So how does write work in MapR? Client writing data usually would be writing to a container at a server and ask for a block and write to that. If the server has containers available, it gives them back. If not, it goes to the name node map and says, create me a container. The name node map might find an existing container or create something new and returns the location, the container and its locations back to the server. The server attaches that container into the list of the file structure, gives it back to the client. Then the client can now directly talk to the server without this. So the name node is contacted only once in a blue moon, whenever it runs out of 32 gig or so. But we needed to implement distributed transactions to stitch these things together, because this is going to get inconsistent very, very fast. So every node has a write-ahead log. When we support both kind of logging, value log, which is really a disk offset, and you write old value and new value at the disk offset. And we also had to implement an operational log, where you keep the op details and you have a undo operation and a redo operation in case things fail. And we implemented this pretty well, so we can recover in about 2 seconds. But we had to implement global IDs to create distributed transactions. So the next question came up was, what kind of distributed transactions to use? So we looked at two-phase commit, which is the most popular one. So what happens in two-phase commit is, when the application says begin trans work and then commit, when the commit happens, the coordinator is at the app, it sends these prepare messages to all the participants. The participants all respond back with the prepare ACK, and at this point, they lock themselves and say, we can neither roll forward nor roll back. They guarantee that, and they give up the right to abort. So the coordinator forces a log and sends essentially commits at that point. The problem is that, as you can see, it's too many message exchanges. And if one of these nodes crashes in the middle, you're pretty much locked up the entire cluster. The other thing we looked at was what Zookeeper and other Paxos or quorum completion things use, which is a quorum completion protocol. And there, it kind of it's similar, but when the commit happens, there's a broadcast done by the coordinator to all the participants. The participants reply. If a majority replies, then the transaction is committed. Otherwise, you go into election mode, and if you can't find a majority, you're pretty much dead in the water. And so the obvious problem here was that the update throughput was very slow, because you need a large number of write replicas, or you need a large number of replicas here. Does not work with n by 2 nodes, and it's kind of monolithic. That is, you can't do really hierarchical things like you can do with two-phase commit. So we introduced lockless transactions, where we pretty much do a begin trans, work, and then commit. And there's no explicit commit, it's piggybacked. And the undo is done by using rollback. And any replica can confirm. So if you have, even if you have cycles like this, the confirmation is done by any replica. So it's pretty crash resistant. And there are no locks held across messages, and the cycles are OK. So how does this perform? So we looked at the small file problem, which requires a lot of transactions to happen. And here's what Apache can do on a 10-node cluster. About 1.3 million files created, which is about 130,000 files per data node. With MapR, the same load, we can go up to 80 million files. We stopped the test at that point. We said it's doing pretty well. And the create rate was about 20x. Of course, if I added 10 more nodes, this graph would move straight up by another 8,000 or 10,000, and then move to the right also by another 80 million. And I just superimposed the old graph on this one, and that's the kind of performance we got. But we wanted to make sure that the data path was also safe. So we added a lot of data integrity in the process, end-to-end checksums, which are not optional. And any client can declare a server bad if it sees a checksum problem. RPC packets also have their own checksums. And the whole system is transactional with asset semantics. And some important data structures like allocation bitmaps are written to dual blocks so that even if one gets corrupt, it's better than a checksum. You actually have two copies. And we have built-in automatic compression, so it feels like that's another checksum right there. Why do we do all this stuff? Well, it helps you to make data import or export really, really easy. All I do is mount it and use it. It's fully real-time, fully HA, and it's very, very fast. Otherwise, this is what you normally have to go through to get data in and out of the cluster. So how does it perform? So here's a streaming performance benchmark. The green bars show what the hardware can do. The graph on the left shows 1 gigabyte a second is the hardware bandwidth. The graph on the right shows what 2.2 gigabytes a second hardware bandwidth. And the blue bars show MapR. The orange bars show one of the Hadoop releases. And we're pretty much close to, I think we can do better. We're kind of close to hardware bandwidth limits here. And we ran 2 sets of tests, 16 streams at 120 gigabytes, 2,000 streams at a gigabyte each, and kind of seemed to do OK. Then we ran a CSB benchmark test on 1 billion 1K records on the same 10-node cluster. With the write-ahead log on, write-ahead log off, seemed to do reasonably OK. You can do about 500,000 records per second insert with the thing off. Random read, doing pretty OK there too. We are able to schedule the IOs fairly well. We have 11 drives per, so we can get about 22,000 reads a second. It's a complete cache miss because the data set is 100 gigabytes per machine, while the machine only has 24 gig. So it's about a 4-to-1 ratio here. And we did 2 different Zipfian and uniform distributions. TerraSort, how do we do here? We ran 2 different TerraSorts at 1 terabyte TerraSort and a 3.5 terabyte TerraSort. None of these are with compression on, by the way. These are all uncompressed data. We're just trying to figure out how well the system performs. And we did reasonably OK here, too. Tried out with PigMix. Again, the blue bars are MapR. The orange bars are Apache Hadoop. And it seemed to be OK in some tests, seemed to be not so OK in some tests. So overall, pretty good. So we were happy. So we decided to release the product. We're fully HA. This is completely with 3x replication and everything. We have a full HA for job tracker, snapshots, and so on. I didn't really have time to talk about all that. It's very simple to manage. I think there's some demos done earlier. And you get NFS as well. Complete read-write semantics. So you can actually run a job and do a tail-F and actually watch it while it's working, instead of having to wait for the job to finish. We have signed the Apache CCLA, so we're going to be contributing a lot of the improvements in the MapReduce layer, certainly, back to Apache. We have contributed a major amount of Zookeeper code that we use, including some Mahout. The YCSB changes we had to make it to run, we're contributing those back. Some HBase fixes we have contributed back. And we'll do this as we go along, see what's, if we get the time, we'll contribute more and so on. Like I said earlier, this is available free, unlimited, unrestricted use. You can download it and try it. I think you'll be happy. If you have a problem, contact us and we'll help you solve the problem. Cool. Any questions?
Yeah, so I got a question here. So I didn't get it. Is it a fully POSIX file system that you're building? Can I run, for example, my secret on it?
Through NFS, it's mostly POSIX. So we don't have hard links. We don't have extended file attributes. We don't have A-time support. But otherwise, it's mostly POSIX, yeah.
So it supports stuff like ODirect?
No.
Right.
ODirect is a local disk thing, right? So no, we don't do that's the NFS client implementation issue. It's nothing to do with the server side.
Got it.
ODirect means sync it immediately, right? Yeah. Any questions?
You support symbolic links?
Absolutely. Support symbolic links. ln-s. And by the way, whatever you can do with on the NFS side, the path names are identical on the Hadoop side. So you can write a script in Python or whatever, and then say, OK, now kick off a MapReduce job, and the path names are identical. So it's 1 for 1.
have two questions.
Yes, sir.
One is about name node. Name node map, is it a single server or distributed, or how single point of failure is solved for that? And second one, how do you address the locality of data?
Very good.
You are sharding.
Yeah, I'll
them.
talk to that both.
So, okay.
So the name node map itself is another container in the system. It's exactly replicated the same way as any of the other data. So as soon as it's three-way replicated or four-way replicated, as soon as we fall below 3 replicas, we start re-replicating it immediately. So it kind of will find any node on the cluster and move there automatically. And if we fall below 2, we stop writes until we make sure that there are at least 2 replicas. For locality of reference, it's exactly the same way we do with HDFS. It's the first copy is local when you do a write, and then the second copy and the third copy are remote for the different chunks. Sorry.
I'm sorry, but locality, it's a different question. So if you're sharding by name, for example, right, then files from the same directory can go into different regions.
Yeah, so the name node is actually 3 different parts, right? There's a file structure and the file contents, right? So that is separated in our system. So the file structure is in the mini name node. The file contents is local to the machine you're running on. So that's why we need the distributed transactions. So we create the file contents in the local machine where you are in. So if you're writing on node A, then the first copy of the file is in node A. The second, third copies are distributed as they run.
2 files in the same directory, right? Can they belong to 2 different?
Absolutely.
Then they're not local.
No, they're local.
Okay.
Yeah, you can have as many files as you want, and the first copy is local. The file contents and the file structure are separated still. Right, so you can still do that. Any questions?
Hi,
Yeah.
this is really awesome work. How much of this is open source, and what are the future plans of, if any?
So this is in C++. It's right now we kept it proprietary. It's free, so you can use it unlimited. We'll put things out into open source as we go along. I don't know which ones we will do it and which ones we won't right now. So we'll have to just see as we go along. There's a lot of things in our system. It's not just the storage system, right? I mean, there's MapReduce and there's other things as well. So we'll make different things open source as we go along. Cool.
Do you have the ability of striping a file between the multiple data nodes? Right, so I call file foo, and the first n number of bytes are on one node.
Yes.
The rest are somewhere
Absolutely. So that's automatic. What happens is that it's chunked or blocked the same way. The first copy of every block is on the name. So there are 3 copies or 4 copies or whatever of whatever your replication factor is. The other copies are striped. They're spread out on the cluster. So the block reports are the one that have been made much tinier. But the blocks themselves, you can have a 64K block or you can have a 1 gigabyte block. It doesn't matter, and it gets striped automatically as you run, both through NFS as well as through regular regular HDFS APIs. Exactly like what happens on HDFS.
Okay. So
it's
when you
out.
say that ODirect is not supported, I mean, it's an NFS client issue, right? So if the NFS client knows how to do ODirect, why is it not supported?
So you have we do the NFS server. NFS client is running on your Macintosh or on your PC or in your Windows Linux box.
Right.
And ODirect means write the data in the VM out immediately and don't come back until you wrote it. So it comes to the server. The server is running MapR. It will write 1 copy local and write the other copies in different nodes and then reply to it. So so the ODirect implementation depends on the NFS client.
Right. So you do
On the server side, it's always ODirect to the raw disk.
Okay.
So there is nothing. There's no VM or anything on the server side.
Okay. So you do support it then?
right?
It's
I mean, it's a
really a
client-side.
client-side implementation, right? It's nothing to do with the server, really.
So it
I
is-
mean, we're not VM integrated, if
All
that's
right,
your question.
good.
I'm afraid that's all the time we have. Thank you.
Okay, thanks.